Hey there. Okay, so we are try out our first attempt at giving an abstract algebra lecture as video instead of you guys being there to hear it live. This is the first time I'm making one of these videos for you guys. Hopefully the quality is going to get better. I mean, I am thinking about things like glare and lighting. I've got a new device on the way. Maybe I'll be doing these things as a screencast where you won't really see me as much as just sort of some writing that's a little bit easier to read, but we're going to try this. I also hope you can hear me. My voice is sounding a little hoarse. Okay, so the topic I want to introduce to you guys today is something called vector groups. It's in the next section, 2.6. In our text, and it's kind of what we've been building up to in our work with cosets. So I want to start by reminding you about something that we've already been talking about. It's kind of a motivational example. So I'm going to try to write this big enough that you can see it, but small enough that I don't have to erase too much. But so let's recall an important example. So I'm going to be talking about the group of integers under addition. And when you pick a certain integer, say a positive one, n, then we've looked at this subgroup. I'm going to recall the notation for it, n times z, and I can write it as a set. It's just the multiples of n. I take n, I multiply it by an integer k. I do it for every possible integer k. So that's the multiples of n. And we know that's a subgroup of z. Z is an abelian group. It's a normal subgroup of z. And we looked at the cosets of this subgroup. If I choose an integer, say call it a, its coset, well, this is an additive group, right? So I should be writing the coset as element, group operation, subgroup name. So that's what a coset looks like in additive notation. The subgroup itself has kind of a flowery name. Here the n and z might even be making you think about a coset, but I don't mean that there. I mean all the multiples of n. The coset is written here with the plus because that's the group operation, and z. And what's in this set? Well, we would just take all these nk's and we add a to them. So these are all the numbers that when I divide them by n, I would get the same remainder as when I divided a by n. We have another name for that. That was just the equivalence class of the number a in the congruence relation mod n. So we've talked about this before, that for this subgroup, its cosets are precisely those equivalence classes. So the set of cosets, here, I'm going to kneel down here so I can write it. I think you can see one more line. The set of cosets of nz in z, well, it's just one for each one of these equivalence classes. We know exactly how many of those equivalence classes there are. There's one for each number between 0 and n minus 1. And that we have made into a group before. Those equivalence classes together make what we call the group Z sub n. And in particular, the operation, I'm going to write it up here in this corner, where we take a class containing A, and we add to it a class containing B by just simply saying, well, it's the class containing AB, that operation was well defined. We worked to prove it. Okay, so I haven't really said anything new yet. What am I trying to say? That we have, in this course, looked at an example of a group. I'm just going to point at the characters while I say this. An example of a group where we take one of its subgroups and the set of cosets of that subgroup ends up itself being a group where we just add the cosets by adding elements that are in them and looking at the coset that contains that sum. So that's this construction that we've seen in this example, the construction of the group of integers under addition mod n. And all of this is an example of what we will call a factor group. Z sub n is an example of a factor group. It's a group that's made out of a set of cosets of a subgroup. And it turns out, and we won't see it in this lecture here today, but that subgroup, it turns out, has to be a normal subgroup in order for all of this to work. So it's kind of hidden in this example because the group Z is abelian. And so every one of its subgroups is normal. But and this would be a good exercise later on when we're done with this stuff, if you went back and dissected the proof where we showed addition mod n is well defined, you would see in there somewhere the commutativity, and in general it would be normal subgroup, but it got used. So we'll try to circle back and see that. Okay, so this is the example I want you to kind of have in mind as we proceed. I'm going to start making some new room. I've got a little bit of room here. I'll try to use it to minimize how much I have to erase. And it'll be nice if we can have some of this stuff on here. So now, motivated by what we were just talking about, let me have some group G. I'll write it multiplicatively. It's an arbitrary abstract group. And I want to take a normal subgroup of it. So recall that that's how we write that. A decorated subgroup symbol means that n is normal. Okay, well, we know, because n is normal, that for every element in this group, the left and the right coset containing that element are going to be the same. That's one of our characterizations of normal subgroups, is that they have the same left and right cosets. So when I'm talking about a normal subgroup's cosets, I can relax and I don't have to say left and right all the time. I can just speak about its cosets because they're the same. Okay, so here's some notation. I'm going to denote by G over N. It'll kind of start to make more sense, but just take it as a definition right now. G over N is just the set of all of the cosets. So it's the set of all things that look like, say, AN, all right left cosets, where A runs over G. Okay, so this is the set of cosets of N and G. Can you guys still see that one down there? Yeah, good. All right, good. Set of cosets of N and G. Just gather them all up. If G is a finite group, Lagrange's theorem says that the number of these things is just the size of G divided by the size of N. It's the index. The number of cosets is the index in general. And for a finite group, you can calculate that index with Lagrange. So I'm just giving a notation for the set of them. Before I erase it, I should say this is an example. Z sub n is the set of cosets of this subgroup in Z. All right, so that kind of maybe gives you a hint of where I'm going with this. I want to make this into a group. I want to make this set of cosets into a group. I want to give it a binary operation that will enjoy all those axioms that groups have. Okay, so yeah, well, we need a binary operation. How did the binary operation work in our motivating example that I'm erasing here? Well, it was kind of the most naive possible idea we could have. I still saved it. You take a coset and you want to combine it with another coset. Well, just combine the elements in the group and look at the coset they're in. That's what this equation says. So what does that look like in this notation? Let's try it. So let me write down what I want. I want a binary operation on G over N. That's what I want, a binary operation on G over N. What could it be? Let's try this. What's an element of G over N look like? Well, it looks like a coset. And I want a binary operation, so I should take two of those things. So maybe A and B are two elements of G, and they're two cosets. And if I just wanted to proceed like this, I'm writing things multiplicatively, but I should say, well, the coset containing A, I'm looking over there, times the coset containing B. Well, can you guess it? Can you pause the video and write it down before I do? What should it be? It should be a coset. And how should I make it? I should make it, well, take A and B and multiply them in the group G and see what coset they land in. Maybe seriously, pause this for a second and think, can you understand this equation that I'm writing down is just the multiplicative analog of this. It's saying the exact same thing in the different notation. Here, I should have quantified. For every elements A and B and G, I'd like to try that. But we have a question here. Is that operation going to be well defined? And what does that mean? It means the same thing over as it did over in the integer case. A, you know, it's not the only representative for the coset. Maybe the coset containing A is also the coset containing, I'm going to call it alpha. It's possible. Maybe B is represented by another element, beta. So, you know, if I'm working with these Roman letter representatives, I'm going to say that the product of these two cosets is this one. And if you are working with the representatives that are written in the Greek letters, you're going to say that the product of those two cosets is that one. And we certainly have to worry about whether, are those going to be the same? That's what well-defined means. If these are always the same under these conditions, then this is a well-defined operation. If not, then it's nonsense. So that's kind of what we have to get done here in this lecture, is I want to convince you that if N is a normal subgroup, this operation is perfectly well-defined. And then the fact that G over N is a group under this, well, we have to say something, but the group axioms will follow immediately, because we've said this before. Look, I'm defining this operation in terms of an operation for which all those properties are true. So nothing is going to stop us. Once we have that this thing is well defined, the fact that this set of cosets forms a group will be the easy part of our work. Okay, so we need to make a little bit of room. Not quite sure how long this is getting, but we'll just try to wrap this lecture up with trying to show that this operation is well defined in a comment about this is a group, why it's a group. And I wrote down a theorem number I can point you to, so when you're checking out your text, you can square all this stuff away. Okay, so let's get right to it. I'm going to use this notation since the board is small. I want to show that this operation is well defined. So I've got a couple of cosets that have different representatives, A and alpha, B and beta. This is the equation that I want to demonstrate. So let's remind ourselves, what does it mean? A and alpha represent the same coset. Let's try to write down what we mean by that. Okay. So the left coset containing A is the same as the right coset containing A. Well, by the definition of coset equality, that means that, say, the inverse of alpha times A with the inverse on the left belongs to that subgroup. That's the definition of coset equality. The equivalence relation. Okay, well, so that means that alpha inverse A is, say, equal to, I'm going to call it N1, because there will be some other ones, for some N1 and N. And this is going to be my last place. If I solve that equation for A, it tells me something, that A looks like alpha times an element in N. This is what I want. And in fact, as a summary, as we work more and more with these cosets, you probably want to work with this enough to where when you see this, when you see two cosets are the same, you can kind of jump right to this, that it means that the elements are equal, quote unquote, up to an element of N. Alpha and A represent the same coset. It means A is alpha times something in N. They're equal up to something in N is kind of the spirit of it. So likewise, if I take that shortcut, if I say, okay, B and beta have the same coset, skipping the intermediate steps, it means that B is beta times something. I'll call it N2. Okay? And then I'm going to try to use the whole vertical bottom here. Trying to get creative on my new workspace. What do I want? I want to show that AB and alpha beta represent the same coset. Well, so I should check out AB. Look, I've got an expression for A. It's outlined in red. I've got an expression for B. Let's check them out. A times B is the same as, well, alpha times N1 times beta times N2, which I'm going to reassociate because I'm working in a group. N1 beta, I'm not taking anything out of order, just reassociating those parentheses. Okay, and nowhere have I said anything about N being a normal subgroup. Now is where it's going to come in, because this part of our product, N1 beta, I'm going to write this in red below it, that is an element of the right coset containing beta. It's a group and a subgroup element times beta. But that right coset is equal to the left coset containing beta, because N is normal. So this element, N1 beta, it equals beta times something else in N. I'm going to call it N3. I can switch the order, but I have to possibly change the group element N. So this product, if I continue, is equal to alpha beta N3 times N2. And this equality, I'm going to write it here. That's exactly where I'm using for the first time that N is a normal subgroup. Okay, so the line is kind of going down, I see, but can you see it? Can you finish it? At the end of the day, I've shown that AB is alpha beta, if we reassociate one more time, times something in N. Let me try to write it here. I don't know if you're going to be able to see it. It's pretty small over there. Maybe you can zoom in. AB is alpha beta times something in N. That precisely means that those two cosets are the same. It precisely means that those two cosets are the same. So this operation on the set of all cosets, call it Coset multiplication. prove to you that if n is a normal subgroup, coset multiplication is well defined. Coset multiplication is addition mod n in that example when g is the integers and n is the multiples of a fixed integer, then that's just congruence. So for it exactly generalizes that idea. Cool. Okay, so let me make a little bit of room here. Hopefully you'll join in a face-to-face Zoom meeting or office hour. You can ask me some questions about this kind of stuff. All that used to working without an audience. So my timing and everything is going to kind of seem a little bit different here as we adjust. We'll make do. So let me write up here, check it out in your book, the theorem number. It's 261. Just write it across the whole surface here. So theorem 2.6.1. It says if G is a group, N is a normal subgroup of G, then the operation AN times BN is ABN. Here, A and B are any two elements of G. Is well defined on G over N, the set of all, oops, pardon me, set of all cosets. And then moreover, this operation makes G over N a group with, I haven't said anything about this yet, but hopefully maybe you will really pause it and see if you can tell me it's a group with identity. Well, it has to be one of the cosets. Which coset is going to act like an identity under this operation of coset multiplication? Well, it's the coset containing the identity. So with the identity En, which you can just simply write as N, and one more that you can fill in, you can pause, for every A and G, what should be the inverse of the coset containing A? Can you pause? Can you guess it? The inverse of the coset containing A should be the coset containing A inverse. So I made the little proof symbol box there like I've proven this, but I'm being a little bit dishonest because what did we prove here in this meeting, this lecture? We proved the operation was well defined. That's actually the entire issue because like we were saying, it's defined in terms of a group operation where all of the axioms will hold. So I am going to assign it to you as an exercise. We can talk about it in a face-to-face Zoom meeting where we're online at the same time. But what remains to really justify that this proof is done? Well, you need to show this operation is associative. Okay, well, it's defined in terms of an operation in G that's associative, so it should be done, but doable, but you need to do it. I claimed this is the identity. It needs to be demonstrated that when you use this coset and this product, that it acts like an identity. And then I've claimed what I know the inverse of something is. You have to demonstrate it. So the well-definedness is done. But the associativity and the fact that the proposed identity and the proposed inverse work, I'm going to leave to you. Okay, so that's probably something to think about here. So we'll call that a day in terms of covering this construction of factor groups. The plan for the next lecture is to look at a whole bunch of examples of these things. Try to get used to working in them. Okay, so maybe I'll see you online.